The next module of our data structure lab. So in this module we are going to look at trees. So basically trees are a non-linear data type structure where the data is stored in a relationship or a hierarchical manner. So the best example to understand what a tree is basically a family. Let this be you at the D element. So B will basically be your parent, A will be your grandparent, C can be your uncle, and further down he can have his children, and furthermore their children. So that is basically how a tree data structure goes. It basically shows a relationship between each of the data structure elements and how the hierarchy is formed between them. So in this module we are going to look at the terminologies associated with a tree. So first up we have the root node. We can define root node as the first element or the first node of every tree. So here we have A as the root node. Every tree must have a root node, and basically a root node, there can only be one root node to a tree. Next up we have edge. So edges are basically the lines, basically these things, lines or the connections joining the nodes or the elements of a tree. So suppose there are n elements in a tree. Suppose this tree has 8 elements. Therefore it will have, suppose there are n elements, the number of edges in a tree will be n minus 1. So they are basically the connections or the lines joining the elements. Next up we have parent and child. So parent and child nodes are parent nodes will be the predecessor to the child nodes, and the child nodes will be the successor to the parent nodes. So here for example A will obviously be a parent node, and it will have B and C as its child nodes. Furthermore down you can see that C can also be a parent node with F as one of its child. Similarly F will also be a parent node with G and H as its children. Next we have is siblings. Similar to real life, sibling nodes are basically the nodes that are from the same parent. So here G and H will be sibling parents as they are from the same. G and H will be sibling nodes as they are from the same parent F. Next we have leaf nodes. So leaf nodes are basically the terminary or the last nodes present in a tree. So basically these nodes or these elements do not have any children. So here we will have D, E, G and H as the leaf nodes, since they don't have any successor or any child nodes. Next we have height. So basically a height of a tree or a height of an element is basically the number of edges it has starting from the leaf node. So for example, the height of this tree, the bottommost leaf node here, as you can observe, are G and H. So the height of this tree counting from G and H will be 1, 2, 3. So this tree will have a height of 3. Similarly, if you have to find the height of a node, for example the node C, you can clearly see that it has 2 edges, or basically 2 lines joining it to the leaf node, so it will have a height of 2. Next up we have path. So as the name suggests, path basically is the way or the route from one node to another, and basically how many lines or edges are required to join them. So basically the path from, suppose we have the path from node F to node C. So you can see it's a direct connection, so the path will only require one edge or one line. Similarly, if we have to find the path from H node, which is one of the leaf nodes, to the root node, we can see that the path will require 1, 2 and basically 3 edges to go through. So the path will basically be from H to F, F to C, and then C to N, and so on. It will be similar for the other elements as well. Next, we have depth of the tree. So basically, depth is the inverse of height. So basically, how in height we start from the leaf node or the end nodes. The end nodes. In depth, we start from the root node of the tree. So basically, if you have to find the depth of an entire tree, again, you will start from the top and basically this will 1, 2 and 3. So basically it will have a depth of 3. Similarly we can find the depth for the elements as well. Suppose we have to find the depth of the element C here. So obviously it will have a depth of 1. It will have a depth of obviously 1 and then basically a depth of 1 because there is only one edge or one connection from the root node to C. Next we have level. So basically a level similar to levels in a building. A level in a tree are basically how many levels of parents or how many levels of nodes are actually present in a tree. So here we'll have the root node at level 0. Next we will have the nodes B and C at level 1. Similarly these nodes at level 2. So basically that's how you establish levels of a tree. Next, so lastly we come to tree traversal. So just to give you a basic explanation, tree traversal is a function of a tree where basically we can access the elements of a tree. There are 3 ways in which the elements can be accessed. There is pre-order, in order and then post-order. In pre-order, basically there are 3 elements. So while accessing a tree, we have 3 things: the left node, the left, the node, and the right. So basically, in order, we first check the left side of the tree, and then we write down the node, and then the right node. But in pre-order, we basically do NLR. Basically, we refer or we skip to the node first and write it down, and then the left side, and then we check the right. Similarly, in post order, the node comes at the end. So basically, we do LRN. So yeah, that's how tree traversal is performed. Next function we have in tree is basically heap function. So what the heap function basically says is, suppose we have basically the root node of the tree will be the highest element, and following it the leaf node will be the lowest element. This applies to each and every parent-child relationship in the tree. Basically each parent or each parent element of the tree will be larger than its child elements. Now we are going to look at the advantages and disadvantages of the tree data structure. So the advantages include that in a balanced tree, it is efficient to basically search, insert or delete elements from the tree, having time complexity O log n. Another advantage is that it follows hierarchical structure. So it is good in, basically appropriate in implementing structures like file system or organizational charts. On the other hand, the disadvantages include if a tree becomes unbalanced, the time complexity for insertion, deletion or traversal functions becomes On, which is like not good for the implementation. Another disadvantage includes the complex implementation of a tree. So obviously, since we learned all the terminologies and everything, we can clearly see that it is much more difficult or much more of a task to implement trees instead of data structures like array or lists.